Hi, Dr. Alanis. How are you?
Fine, thank you. Hello. Long time no see.
Nice to meet you again. Can you hear my voice? Hello?
Yes, I can.
Okay, I also can hear your voice. We also have Dr. Titi. He is head of my research group. Maybe you can present yourself to Dr. Titi.
Yes, Dr. Alan is already joined at 9 o'clock, 50. He must have misunderstood the time difference between Jakarta and which is the location? Philippines or
Yes, Philippines. Yes, in the Philippines. I'm currently in Manila right now because of I had to attend some meetings with our collaborators.
You are still contact Dr. Yama, ya, Dr. Alanis?
Yes. I think he is now in with the Geological Survey of Japan.
Yes. Recently, I contact him related to the 3D modeling, but until till now we didn't solve our problem related to 3D. How about you in Philippines? Phoenix, Indonesia, informed me that your institute just use MTU 5C. Is it right?
Yes, we got a new. As you know, back in 2020, there was an eruption in Taal, and I think our MTU-5A unit got hit by an electromagnetic pulse during the eruption. And according to Phoenix, it got broken.
Oh, yeah.
So I think that it was affected by the eruption, because during the eruption there was a lot of volcanic lightning that occurred. So although it was secured in the observatory, we had to evacuate because it was getting dangerous. We were quite close to the volcano. So I think during the eruption, a lightning strike hit the observatory, and one of the equipment that got damaged was the MTU instrument. So we had to get a new one, Phoenix MTU-5C this time.
Wow.
But we're still right now we're still learning how to use it, because it's a different instrument.
Yes. Also, the Phoenix Indonesia asked for me to ask you, how about the condition of the MTU-5C in Philippines? Because as I know, the equipment is a long period until what the frequency may be the long term for the MC. So the condition is fine in your institute, the MTU-5C?
Well, actually, we haven't used it yet in the field. We're still learning. It just arrived late last year, so we're still in contact with Phoenix. What changes they what procedures follow? Because the old manual is no longer. Because the manual we have is for the MTU-5A.
Yeah. Also, the software is new one. So actually, yesterday, Phoenix Indonesia also presentation in our institute. They also presented about the new one, the MTU-5C, and I think all software is new, so we cannot use the MC editor again. For the MTU-5C, we must use the new software like Empower. The name is Empower, yes. So I think if we buy the MTU-5C, we also must buy all new software.
Yes.
Yeah. We still have 5 minutes, Dr. Alanis, to invite participant, also our head of the center. Please wait a moment.
Okay, it's all right.
Berarti
Titik, Pak Adrin sudah masuk, mau dimulai atau tunggu lagi 5 menit, 10 menitan?
Oke. Mungkin udah jam 10 Ibu Fatih, mungkin kita mulai saja ya.
Keluar lagi nih Pak Adrinnya.
Hah?
Nggak ada lagi Pak Adrin. Keluar kayaknya. Sinyal memang. Tadi sempat masuk tuh Pak Adrin. Mungkin kita tunggu Pak Adrin sebentar ya. Lagi usaha masuk loh. Untuk seluruh peserta, kita tunggu sekitar 5 menitan lagi ya, sambil menunggu ini ada Pak Adrin, Kepala Riset Center Pusat Riset Kebencanaan dan Geologi yang sedang di lapangan dan sepertinya terkendala sinyal. Tunggu sebentar ya, sekitar 5 menitan baru kita mulai.
Pak Adrin sudah datang Bu Fatih.
Sudah hadir ya Pak Adrin ya?
Pak Adrin sudah hadir.
Oke. Oke, selamat pagi semuanya, teman-teman mahasiswa yang sudah berkenan hadir di seminar hari ini, dan seminar webinar pagi ini kita sampaikan dalam bahasa Inggris ya, karena kebetulan pembicaranya dari Filipina. Okay, good morning everyone. Thanks very much for all participants. Today we will conduct the webinar conducted by the research group of the Crustal Structure and Dynamics as the part of the Center of the Geological Disaster BRIN. Today we are having Dr. Alanis. Before I read this curriculum vitae, firstly maybe there is welcoming speech from our head, the head of the Research Center for the Geological Disaster, Dr. Adrin Tohari. Please, Dr. Adrin Tohari, time is yours to welcome, to present your welcome speech before the today webinar. Halo, Pak Adrin. Silakan, Pak Adrin.
Thank you very much for the... Halo?
Iya, suaranya
Sudah terdengar belum? Ini
Sudah
sinyal
terdengar.
saya kurang bagus ini. Sudah terdengar belum?
Sudah, Pak
Ya,
Adrin,
Pak.
sudah terdengar.
Clear, Pak.
Putus-putus ya suara saya ya? Break up ya?
Enggak, Pak. Enggak ada delay kok, Pak.
Okay, I will try. Okay, siap. Okay, thank you very much, Miss Moderator. Good morning, everyone. Good morning, Dr. Paul Carson. Nice to meet you, even though we met virtually. On behalf of Research Center for Geological Disaster, we thank for your presence in this webinar. For your information, our research center was established last year on March 2022, and we have about 104 researchers from different fields of study, such as geology, engineering geology, geophysics, geography, and remote sensing. So in this opportunity, we'd like to learn from you about geophysical study on volcanoes. So we hope that your lecture will have, I'm sure that your lecture will have a significant benefit for our researchers. So without well, I give the time for you to start to give the lecture. Thank you very much.
Okay, terima kasih Pak Adrin. Thanks very much for your welcoming speech before the today webinar. And also I want to thank to Dr. Yunus Daud. Thanks very much for your participation in our today webinar. And before Dr. Alanis present his speech, his research, firstly I will read his curriculum vitae. His name is Paul Carson Belmonte Alanis. His PhD degree was from Tokai University, Japan. He is now working as resident volcanologist in Mayon Volcano Observatory, Philippine Institute of Volcanology and Seismology, and also he has some publication related to the volcano by using some geophysical methods like microgravity, INSAR, and Magnetotelluric methods. Today, his presentation entitled Resistivity Structure and Eruptive Behavior of the Taal Volcano explained from Magnetotelluric observation. Dr. Alanis, you have time about 45 minutes for your presentation, and 30 minutes later we have discussion session. Time is yours. You can share your presentation, Dr. Alanis.
Okay, thank you, Dr. Febti.
Okay.
Can you see the screen now?
Yes, sure.
Okay, thank you very much. So again, I am Paul Carson Alanis from the Mayon Volcano Observatory, the Philippine Institute of Volcanology and Seismology. I am also the concurrently as Taal Volcano Observatory officer in charge. Now, today I will talk about our research back in the before the eruption of Taal Volcano in January 2020. So this was the resistivity structure and eruptive behavior of Taal Volcano explained from magnetotelluric observations. Okay, so to understand so I'll first talk about the tectonics of the Philippines. So to understand the tectonics of the Philippines, it's basically we have to take into account the interactions between three or four major plates. There is the Pacific and Philippine Sea plate in the east, moving northwest, and then there is the Eurasian plate moving southeast in the west side of the Philippines. And in the south of the Philippines, there is the Australian plate, which is moving north. Now, moving on to the more detailed geology and tectonics of Taal Volcano. So Taal Volcano is related to the subduction of the Eurasian plate underneath along the Manila Trench, and it is Taal Volcano itself is found at the intersection of the north-south trending West Luzon volcanic arc and at the northeast-southwest trending volcanic spreading zone called the Makulod Corridor. So, Taal Volcano itself is found in the island of Luzon, in the northern Philippines, and it's quite close to the capital of the Philippines, Metro Manila, only about 60 kilometers south. And the Taal Volcano itself, right now, is found inside a large caldera formed about between 5,000 and 100,000 years ago, and it's now called Taal Lake. And basically, in terms of topography or physical description, Taal Volcano is a rather small volcano, or at least in terms of height. The maximum elevation is only about 300 meters above sea level. Now, in the center of Taal Volcano itself is another caldera, which is called the Main Crater Lake, or now we will call it the MCL. And because of its frequent eruptions, which are sometimes very deadly, back in the 1990s, it was declared as one of the decade volcanoes by IAVSE. So, what is the rationale for studying and monitoring Taal Volcano? So, as a brief backgrounder, the Philippines has about 300 volcanoes.
Recording in progress.
But only 24 of those, out of the 300, are considered active. So, PIPOX itself, our institute is a rather small institute. So, currently, at the moment, we only monitor, out of the 24 active volcanoes in the Philippines, we only monitor about 10 volcanoes. And one of those volcanoes is Taal Volcano. So why do we monitor that? Firstly, because of the frequent eruptions of this volcano. Since the first observed recorded eruption in 1572, there have been about 30 plus eruptions. The last one was in 2020. And currently, until now, there's still some abnormal behavior with the volcanoes. Now, these eruptions of Taal Volcano are of the very explosive and extremely hazardous, of the phreatic and phreatomagmatic type of eruption. And unfortunately, these eruptions frequently claim a lot of lives. In one particularly large and violent eruption in 1911, 1,300 people were killed. And the last eruption that caused casualties was in 1965, which is about 200 people killed. And lastly, because it's very close to Metro Manila, which as of 2018 has a population of about 14 million. And the immediate area surrounding Taal Volcano itself has a population of about 8 million. So these are some of the eruption hazards exhibited by Taal Volcano during an eruption. We have ash falls and ballistic projectiles, some lava flows, base surges, which was first observed in Taal Volcano in 1965, seishes or lake water oscillations, and sometimes flooding also occurs. Ground fissuring and ground subsidence was observed during eruptions of Taal Volcano. And during the rainy season, landslides, lahars, and mud flows are sometimes occur. And lately, also toxic volcanic gases are released by Taal Volcano until now, sometimes last year reached about 30,000 tons, or sorry, 25,000 tons of sulfur dioxide was released in one day last year. So we can divide historical eruptions of Taal Volcano into about four series. So the Series A eruptions occurred at the main crater from 1572 to 1645. And then after 1645, most of the eruptions are now found at the flanks, and no eruptions occurred at the main crater. So in 77, in 1707, in the northeast flank of the volcano, up to 1731. And then come 1749 up to 1911, most of the eruptions again returned to the main crater. And then after 1911, most of the eruptions are concentrated again at the flanks. So what does it show? So there seems to be a pattern wherein the eruption center is moving around the volcano, and frequently from main crater or to the side or to the flanks. So these are some previous geophysical studies to find out what the structure of the volcano is. So in 1975, Professor Yokoyama did some gravity measurements across the volcano, and he found some high gravity anomaly underneath the Taal caldera. And then using local geological mapping, Masigla and Ruelo in 1987 hypothesized that there is a large magma chamber under the Taal volcano, which feed not just the main crater but also craters at the sides of the volcano. And then in 1994, some Japanese scientists did some explosion seismology experiment at Taal Volcano Island, and they found a low velocity zone underneath the main crater at about 1.5 kilometers depth, and a reflector at around 6 kilometers depth, which they again hypothesized to be evidence for a magma chamber at that depth. And some recent geophysical studies back in 2012, Ficos et al. They found that there are hydrothermal fluids below the main crater lake, which feed the active geothermal fields on the northern slopes of the volcano. So back in 2005, PHIVOX started using electromagnetic methods to monitor Taal Volcano. So back in the period during 2005-2006, we found rapid changes in the total magnetic flux and the self-potential fields on Taal Volcano Island. We also observed during this time there was an earthquake swarm, and then also withering of the vegetation and increased bubbling at the main crater lake. And then back again in 2010 to 2011, there was again peaking of the seismic activity in Taal Volcano Island. So again, there were people right now. Back then, there were still people living in the island, and we had to evacuate the people because it was thought that there might be an eruption imminent. And some gas surveys across the island showed there was a large amount of carbon dioxide gas emitting or coming out from the main crater lake. And then around 2013, things started to calm down in Taal Volcano, but we thought maybe something is going to happen soon. So again, in January to February 2015, large earthquake swarm occurred for about a month. And then after that, in 2020, there was a large eruption. So the objectives of the study back in 2011, 2012 was to firstly identify the size and the position of the hydrothermal reservoir, which we hypothesized, our group hypothesized to be controlling the eruption behavior of Taal Volcano. So the hydrothermal reservoir, or HTR or HR, is an area or zone where hot volcanic fluids accumulate underneath the volcano. Another objective was, of course, to search for evidence of magma. And for that, we used the Magnetotelluric method to create a three-dimensional resistivity model. And it was hoped that this study will contribute to the understanding of the past. For example, we want to answer the following questions, such as why are the eruptions of Taal moving around, not just concentrating at at just one crater? Second is, why are these eruptions very violent? And then, of course, we want to know, of course, I think almost all of us want to be able to predict when the next eruption will occur or when the next earthquake will occur. So it was hoped that we would know if is Taal gearing up for an eruption, and what is the future volcanic activity of this volcano. So to just give a brief background of the Magnetotelluric method, so it is a passive method using natural, although sometimes you can use artificial sources, using electromagnetic signals coming from the atmosphere to determine resistivity at various depths of the Earth. You utilize lightning, sunspots, and other disturbances in the magnetic field to create, which can induce electrical currents, or the so-called telluric currents. So this figure shows some electrical resistivity, various electrical resistivity properties of rocks. So crystalline igneous rocks tend to be very high resistivity. Sedimentary rocks tend to be in the middle. And then magma has about very low, of course, very low resistivity. Almost the same as water or seawater. So in 2011 and 2012, as part of a multi-parameter study of Taal Volcano, our group did a magnetotelluric survey of Taal Volcano Island. So for this, we used the Phoenix Geophysics MTU-5 and MTU-5A instruments. So this map shows the points that we occupied during the surveys. So the red squares are the points we occupied in March of 2011, and then a year later we came back, and these are the blue squares are then the sites that we occupied in 2012. So why did we choose magnetotellurics to create the structural model of Taal Volcano? So firstly, it has some advantages, especially for Taal Volcano. Firstly, it's quite economical. For the survey, we only used 2 instruments to occupy 34 observation points. And since the measurements need not be simultaneous, it's very cheap. Unlike, of course, if you use seismic, for example, seismic tomography, you would need a lot of seismometers, and then the observation has to be simultaneous. The second advantage is the ease of deployment. So firstly, Taal Volcano is quite small, and the topography is very gentle. and the highest point is only about 311 meters above sea level. So it's quite very useful, even though sometimes we have to use horses to carry the batteries, which are quite heavy. And then, although magnetotellurics or any electromagnetic method is very susceptible to electromagnetic noise, Taal Volcano is very isolated since it's in an island. Since it's an island, and there is a lack of commercial electric power, so we can do observations for a very long time, more than 24 hours. And because it's a diffusion equation based, we can obtain good resolution between from a few hundred meters down to a few kilometers depth. So these are some examples of magnetotellurics as applied in other volcanoes. So Nur Hasan in 2006 created a sorry, I think there was an earthquake. Anyway, in Kusatsu Shirane volcano, Nur Hasan created a resistivity model of the volcano. And in 2009, Yamaya also created a resistivity model for Tarumai volcano in Japan. So for the processing, because I will not go into detail on how we did this, but these are the steps we used. Firstly, we created a one-dimensional model using Occam's one-dimensional inversion. Second, then we proceeded to use two-dimensional inversion using Uchida and Ogawa's code in 1984. This one uses the least squares inversion method. And finally, after creating the two-dimensional model, we proceeded to use Fomenko and Mogi's code of 2002 to create a three-dimensional volcano using the result from the two-dimensional inversion. So, however, during the course of the analysis and processing and analysis, we found that although the MTU5, we used a hybrid method of combining the MTU5 and MTU5A data, so that we could measure from 0.001 hertz up to 100,000 hertz. Unfortunately, the purpose of that was to get very deep penetration, and therefore create a deeper model, the resistivity structure. However, during the course of the analysis, we found that at around 0.01 hertz, the induction vectors, which are supposed to point to a conductor, are all pointing towards the southwest. So we think that there is a very large conductor, particularly we call the Verde Island Strait, this green shaded area to the south of Taal Volcano, is acting as a very large conductor. So this limits our model in the sense that we can only use the frequencies above 0.01 hertz, and therefore the model that we created only goes down to about 6 kilometers depth. So after that, after all that modeling, this is the resistivity model that we came up, or we found. So note that this magma and this black body, or the magma, is not to scale. So we don't know where this actually is. So you can only take the model. The model created up to about 6 kilometers depth. So what we found after modeling was that there is a hydrothermal reservoir, this green zone underneath Taal Volcano, or rather directly underneath the main crater. This is a large zone of high resistivity, and this is what we think is the hydrothermal reservoir. So in terms of dimensions, we think this is about between 1 and 4 kilometers, found between 1 to 4 kilometers depth, between 2.5 to 3 kilometers wide, and about 3.5 to 4 kilometers long. So, and at least 3 kilometers thick. Now, in terms of physical properties, we think that this hydrothermal reservoir is very porous and filled with volcanic fluids in both a gaseous and liquid state, and coming from these volcanic fluids are likely coming from a stagnant magma body at depth. And over this hydrothermal reservoir, there is an impermeable layer of clays about 1 kilometer thick, starting about 100 meters down to about 1 kilometer in depth. So this hydrothermal reservoir is likely related to the past and even to the future eruption activities of Taal Volcano. So what are the implications of this result? So firstly, the 100 ohmmeter value of this hydrothermal reservoir has a value about 100 ohmmeter. Is about it means that it's primarily made up of clay mineral or some alterations of clay minerals full of interconnected cracks and voids. So it's probably like the structure is likely like that of a sponge, and it's filled inside these cracks and voids are volcanic fluids in a gas and liquid state, or that is a two-phase state. The temperature is likely greater than at least 200 degrees Celsius. Now, the gas phase of the liquid can also explain the value of 100 ohmmeters in this hydrothermal reservoir. And the liquids are present because one, this hydrothermal reservoir is connected to firstly Taal Lake outside of the volcano, and also the main crater lake. Second observation that we found from geochemistry is there's very little sulfur dioxide, so almost zero sulfur dioxide emitted around the hydrothermal vents in the volcano. And it can be explained by the reason that sulfur dioxide is very soluble in water, so it's likely inside either in the hydrothermal reservoir or at the main crater lake. And then some observations also coming from seismology group found that there are some shallow long period earthquake events in 2010 and 2011 that occur in the conduit which connects the hydrothermal reservoir to the main crater lake. So these long period events are likely due to the oscillation of a crack filled with vapor. Now, but then where do these volcanic fluids come from? So these likely come from a stagnant and congealing magma at depth, plus some meteoric and lake waters. So the next significance of this result is that the reservoir size can also explain the shifting of eruption centers and the long intervals between eruptions and the large and destructive eruptions. And the two reasons for that is it takes a long time to fill the hydrothermal reservoir, sometimes takes about 100 years. And then it also explains why there are two cycles of eruption, wherein one eruption cycle begins with an eruption from the main crater, which then ends with eruptions at the flanks. So from 1572 up to about 1731, it's about 104 years. And then so we did this study back in 2012 or 2013. So we think at that time something may happen very soon. So about a few years later, there was an eruption that occurred at the main crater in 2020. So the next question is, why is the hydrothermal reservoir resistive? So this is likely due to the presence of dissolved carbon dioxide, in that for water containing a large amount of carbon dioxide, which is in a two-phase gas and liquid state, is quite stable at about 180 degrees Celsius, which is similar to our result that the HTR, hydrothermal reservoir, is about 200 degrees Celsius. So this carbon dioxide is also likely also influences the behavior of Taal Volcano. So prior to 2020, there were several episodes of what we call false starts of an impending eruption. So in 2005, there was a large swarm, but nothing happened. And then again in 2010, 2011, there was another swarm occurred, and there was we also detected inflation and deflation episodes, which from modeling from subsequent modeling likely came from inflation and deflation of the hydrothermal reservoir. So in 2018, one of our colleagues, Dr. Slotnicki, created this model to explain the reason or what happened during the 2010 and 2011 crisis of Taal Volcano. So he divided the phases of what happened at that time into 4 or rather 5 phases. So phase 1, letter A, is there was a deep inflation source at around 5 kilometer depth, which is similar to the depth of our hydrothermal reservoir. And then phase 2, there were some fluids came to a shallow depth of about 2.5 kilometers. And then phase 3, or letter C, or rather phase 3A, letter C, the fluids expand into the hydrothermal reservoir, which was detected again by ground deformation instruments. And then come phase 3B, our geochemists detected carbon dioxide escaping from the main crater lake and some vents, hydrothermal vents on the slopes of the volcano. So this escape of carbon dioxide was detected twice in 2010 and again in 2011, which coincided with the seismic crisis at Taal Volcano. But again, at this time, no eruption took place. So let's look at an eruption, particularly violent eruption of Taal Volcano in January of 1911. So previously they classified this as a phreatomagmatic eruption, but later on from our study, we think that this is a very different eruption. It's not a simple phreatomagmatic type of eruption. So some characteristics of this was there was particularly strong earthquakes both before and during the eruption. Some of these earthquakes were felt even in Manila, 60 kilometers away. And then at around 2 in the morning of January 30, 1911, there was a large and particularly violent explosion, which ejected mud up to about 10 kilometers away from the crater. Now, this mud was particularly corrosive. There were reports of chemical burns among the victims, including on vegetation, which leads us to surmise that this mud is likely coming from the hydrothermal reservoir, which is likely very acidic. And then we also, of course, back then there was no ground deformation observation, but there were some pictures, and then we can deduce how large the deformation was. So after the eruption, there was ground subsidence between 2.5 to 3 meters, which really from ground deformation from MOGI modeling that we did, we think that this is due to the hydrothermal reservoir shrinking and becoming emptied. And then from petrological studies, we found that there were only very small amounts of juvenile or rather fresh magmatic material from this eruption. And though this leads us to surmise that what occurred was not a simple phreatomagmatic eruption, but rather what Lawless and Brown calls a magmatic hydrothermal eruption. Now, this is very different from a simple phreatomagmatic eruption in that the primary driving force of the eruption comes from the hydrothermal reservoir with very minimal input from magma, which explains the relatively low juvenile magmatic material present. So this is this is timeline from the 2020 eruption. So back in 2019, early 2019, first quarter 2019, we noticed that again there was increasing seismic activity along with inflationary episode of Taal Volcano, along with, of course, increasing carbon dioxide emissions, the hydrothermal vents. And then in 2020, we repeated the advisory or the warning that there's some abnormal thing happening at Taal Volcano. And then after this, in January, on the morning of January 12, there were a lot of volcanic earthquakes occurring. Some of these are felt up to intensity 2 or intensity 3. So at that point, we told the local government officials to evacuate the residents of Taal Volcano. And then at around 1 p.m., there was a small eruption, phreatic eruption, only about 20 meters high. This was caught by our camera inside the main crater lake. And then after that, it continued. The activity continued to escalate. There were continuous earthquakes, continuous tremors, booming sounds, and then of course the tilt meter was really going very high. And then at night, of course, after that, at around 7 p.m., the eruption column already reached 15 kilometers high, and there was also lots of volcanic lightning occurring. And then some observers or some witnesses note that there's a wet ashfall. The ashfall coming from this eruption was very wet. Okay. And then after that, it continued. And then the next day, of course, we did some sulfur dioxide measurements. We found that now after the eruption, we were able to detect sulfur dioxide coming from the volcano. Okay, so anyway, this is the IP camera footage from the main crater lake on the morning of January 12, between 1 p.m. and 3 p.m. Okay. So that's the footage inside the main crater. And then this is the footage from the Taal Volcano Observatory at around the same time period. And this video taken by a vlogger from the vantage point is to the north, on the northern rim of the Taal caldera lake. Okay, so to summarize the eruption characteristics of the January 2020 eruption, we have continuous tremors and earthquakes. Some of these are felt. Very large eruption column reaching up to about 15 kilometers high. There was also volcanic lightning, and of course, one of the observed occurrences was the ash fall that was coming down was very wet. And then there was lava fountaining did occur, but it was very minimal, only lasting a few hours in the morning of January 13. And then immediately after the eruption, lake waters, especially on the mainland side, actually receded, which could mean that the volcano island, and even until now, volcano island, actually some portions of the volcano island went down or became submerged, which means that there was volcano island came deflated. It likely became deflated. And then after 2020 and continuing until now, sulfur dioxide became more abundant, not only became detectable, but became very, very abundant, sometimes reaching in last year up to 25,000 tons in single day. But before 2020, there was no sulfur dioxide detected at the volcano. So this is what we think is, or what we think is happening, or happened at the Taal volcano for the past during its past eruption. So of course, magma intrusions continue, but then at around a certain depth, the magma intrusions are stop, and then these intrusions became congealed, and then some degassing of this magma is occurring, and most of these volcanic gases, or rather liquid in both liquid and gas phase, accumulate inside the hydrothermal reservoir. And then every now and then, of course, some magma manages to reach the surface via the flanks, and we get the flank eruptions. But back in 1911, and possibly before, especially during main crater eruptions, something happened. Probably a small amount of magma managed to disturb the hydrothermal reservoir, which then breaks the impermeable caprock, which is confining the hydrothermal reservoir underneath the volcano, and we get a main crater eruption. So to summarize, the large hydrothermal reservoir found underneath Taal Volcano actually controls its volcanic activities. And then an injection of volcanic fluids into the hydrothermal reservoir can result in sudden inflation or even instability of the hydrothermal reservoir. And then we think that these fluid injections occur repeatedly and fairly regularly, such as in 2010, at least confirmed in 2010, and possibly in 2015 again. And unfortunately, for our study, was not able to find the magma chamber because of the electrical contamination from the Verde Island Strait. And the short-lived lava fountaining in 2020 is likely evidence of only a small amount of magma involved during the eruption. So most of the eruption energy that occurred or that was released in January 2020 likely came from the injection of the hydrothermal reservoir. So it is likely another example of a magmatic hydrothermal eruption. But of course, we have still several questions that we want to answer. For example, why is there no sulfur dioxide gas in Taal prior to 2020? Is it because there is no large magma batch, or is the sulfur dioxide accumulating inside the hydrothermal reservoir? And then, is there a pathway for carbon dioxide gas underneath Taal Volcano? And then, because we were able to detect, and until now we're still detecting carbon dioxide. But then, from what depth does carbon dioxide come from? And if we can answer that question, we could probably answer the next question, which is, what is the depth of the magma chamber? And for future works, of course, we want to continue broadband magnetotelluric observations around Taal Volcano. And hopefully this year we can again begin empty measurements, at least reoccupy the old sites that we occupied in 2011 and 2020 to create a comparison between the resistivity model in 2013 versus post 2020 eruption. So I think that's the last slide. Thank you very much. I'm ready for some questions.
Thank you very much, Dr. Alanis, for your presentation. Actually, this is the interesting presentation. As we know, in Indonesia, we also have some volcano. Maybe the geological setting of the Taal volcano somehow like the Krakatau volcano, I think.
Yes.
And yes, like a Krakatau volcano. And as we know, also in about 1919, the Krakatau volcano also erupted. And for your information, we have about 100 participants. Maybe, if you all participants want to ask Dr. Alanis about presentation about magnetotelluric methods or about how to use the MT for the volcano, you can raise hand to ask. Dan juga jika masih belum bisa menggunakan bahasa Inggris, bisa bertanya dalam bahasa Indonesia. Saya akan coba mentranslate supaya kita komunikasinya dua arah ya. Bisa dengan raise hand atau dengan menulis di chat room. Okay, for the first one, Dr. Yunus. Okay, Dr. Yunus, how nice to meet you again, Dr. Yunus. You can ask Dr. Alanis, Dr. Yunus. Okay, Dr.
Okay.
Yunus, Dr. Alanis, Dr. Yunus is one of the geophysicists in Indonesia. His expertise also about geothermal, hydrothermal, and so on.
Oh, okay.
He is my
Scared.
senior. Please, Dr. Yunus.
Oke, terima kasih Ibu Fepti. Nice to see you also. Good morning, Dr. Paul Alanis. Nice to see you even using this online media. Yeah, hopefully sometime we can see directly and then discuss important thing related to the magnetotelluric or other thing. Okay, this nice presentation, excellent. I enjoy your presentation. I have some question to be confirmed. Just small question. Based on your research in this volcano, what actually the empty role among others? I mean, geoscientific like geochemistry, geology, and other data. My question is related to the empty role based on your research. What the optimum of the empty role in this case to investigate the volcano? This is okay. This first, I have other question later.
Oh, okay. So from what I understand is what is the role of the MT? Okay. So actually, after so earlier I said that in 2005 we started electromagnetic observations in Taal Volcano. So actually, before the eruptions, there was a time when we had about seven magnetometers installed around the volcano. These are taking magnetic measurements real time, and one magnetometer was of the flux gate type magnetometer, and we use that as a real-time magnetotelluric instrument. We were monitoring the stability of the hydrothermal reservoir, which of course is, as we already said, as we stated, around 100 ohms. So so we were monitoring the resistivity. So any changes in the resistivity could mean that the stability of the hydrothermal reservoir is being changed, and could likely lead to an eruption. Unfortunately, we installed this in 2010. By 2019, due to the environment, most of these already broke down. Those that remain, especially if you look at this, look at the video, some of these instruments we already broke down and no longer existing. This small pole in front of the solar panel is actually a magnetometer, which we installed inside the main crater. And then there's another magnetometer further forward of this Oberhauser type magnetometer and a proton magnetometer. Unfortunately, some of these two were already destroyed, so we could not recover the data. So unfortunately, we missed the eruptions because of wear and tear of the instruments. But again, we were monitoring the hydrothermal reservoir prior to the eruption.
Okay, thank you, Dr. Alanis. Concerning the magnetotelluric, did you do MT monitoring or just temporal monitoring? Okay, fixed.
Only temporal.
Yeah, temporal.
Yes,
yeah.
Only yes. But
How many? How many points? How many stations?
34 points. 34 points.
34. Yeah. Okay. And the interval?
This is the
Between two
map
stations?
of the
Okay.
between
yeah. Okay.
800 and around 800. This is the map, shows the points. So about
Okay.
between 800 to 1 kilometer or between 600 to 800 kilometers per the distance between points.
Okay, but between two lines, probably.
Between two lines, about
Distance.
1 kilometer. The spacing between lines.
Okay. And okay, concerning the inversion. Okay, before inversion, what kind of the data? What kind of data quality? Is it good or excellent?
Okay. Okay. Well, of course, there were some times where there was the presence of dead bands. But in general, because again, there's a lack of electrical power, even DC, the data quality was actually very good. So there's not much contamination. Yeah.
The noise is low.
Not much, yes, very low.
Okay, that's good. Okay, concerning the inversion, did you do 3D inversion or?
No, we were not able to do the 3D inversion. This is just forward modeling.
Okay, forward modeling, 3D?
Yes, it's 3D. So it's quite tedious just because you have to add these resistive blocks by yourself until you get a matching, until you match the sounding curve.
Yeah. Okay.
So of course the plan, the plan was to create 3D, three-dimensional model.
Okay, that's good. Yeah, I think that's possible to do 3D inversion.
Yes.
Bufetti, I think this is very, very important. That's good result actually, as Dr. Alanis said, that the noise is very low in this island, so that's good for the 3D inversion. Yeah, probably in collaboration between Brilliant UI. Okay, yeah, actually I'm from University of Indonesia, from Geothermal Research Center, and focusing, especially in magnetotelluric, and I did many data from especially from geothermal areas using 3D inversion. Okay. The last question, sorry, Bu Fetty.
Silakan terakhir, Pak.
Okay, yeah, okay. Could you show again the island and then empty points?
No.
Yes. This island surrounded by sea water, right? So
fresh water. It's actually fresh water.
This is fresh water, not sea water.
Yes. Actually, the island is okay. Let's go back. Okay. Okay. So.
Okay.
This is Luzon Island, and then there is a caldera, and then inside the caldera is Taal Volcano.
Okay.
And then inside Taal Volcano is another lake, main crater lake.
And your measurement above the inside island, right?
Yes, only on the island.
Okay.
So that's what is constraining the model. So the plan after this was supposed to be, we were supposed to do measurements outside to at least minimize the effect of the conductor, which is the very island strait. But the eruption occurred. So it's not. We have to start all over again.
Yes. So this we call coastal effect or lake.
Yes.
Lake water effect is very significant to affect the empty data. So I think better to do we call coastal effect reduction, or removal. I did a couple data for the coastal effect, and the result is a very significant difference.
Nice.
Okay, that's interesting. Okay, good. Congratulations, Dr. Alanis. Thank you for your discussion.
Okay, thank you very much, Dr. Yunus, for your question. So we can discuss many things related to the Taal Volcano and Magnetotelluric with Dr. Alanis. And the next one, also the raise hand, Dr. Mudrik, raise hand. Please, Dr. Mudrik, time is yours. Okay, Dr. Alanis, Dr. Mudrik is one of researcher in our center. Please,
hello, can you hear me?
Yes.
Okay, thank you very much for the time and for the opportunity. And also it is very nice and a good presentation from you, Dr. Alanis. I'm very happy to her and having you here. Okay, and my question is actually that's a following of the previous questions. This location is particularly in the giant of the Taal lakes, correct?
Yes.
So, is that possible that your research is actually has a limitations, and then the chamber could be bigger than the actual size? Because of according to the shape of the volcano, it's very interesting. It's a big caldera, and then that means also the volcano actually has a bigger, and then you only focus on the small crater, small volcanoes in the center. So that's my questions. How is limitation in this study? Thank you.
Yes. We recognize that limitation, especially after finding that most of the induction vectors are pointing southwest towards the sea. So the plan was to increase the points and take measurements on the caldera rim outside of Taal Volcano Island. So yes, at least minimize the coastal effect. So, and one of the reasons why we did this was to find the magma chamber. Unfortunately, due to time and budget, we were only able to make measurements inside on the island itself. So the plan was over the next few years, we make measurements outside. But unfortunately, time caught up with us, and eruptions occurred, and so it's fairly useless now to do some measurements. So right now, the plan at the moment, Taal Volcano is very unstable. So every now and then there are some eruptions, small eruptions taking place. Just last year. You notice the last slide I showed was a footage of the lake, of the main crater lake. That eruption occurred 1 week after we installed, I was part of the group that installed the camera. So it's very unstable, and the gas, the sulfur dioxide emitted was very, very high at that time. Up to 20,000 tons was emitted on that day. So it was very difficult to breathe when we were installing that. So hopefully this year, Taal would become more stable. Then we can again start taking measurements of MT and other electromagnetic methods.
Okay, thank you.
Welcome.
Okay, maybe someone want to ask Dr. Alanis. You can raise your hand or you can write your question by using the chat room. Okay, while waiting some question for you, Dr. Alanis, maybe the question from me. After the 2013 or the before the first one field work of the Taal volcano. After that, there is or no some other field work by using the MT? No.
No.
Not yet. Okay, maybe I think it is interesting to compare if by using your MTU5C, so we can compare the before modeling by using the before fieldwork and after the some eruption after after the 2013 fieldwork, I think.
Yes. So yeah, this year hopefully the condition of the volcano becomes more stable. We can again go back to doing measurements. At the moment, it's very unstable. Recently, to get samples, water samples from the main crater lake, we have to use drones to get water samples. And last year, we started doing total magnetic flux measurements, but only on the coastline because it's very dangerous to climb towards the crater. So hopefully this year it will become more stable and can start to take this time MT measurements.
Yes. The next future, your observatory have or not a plan to build monitoring equipment monitoring by using the MT? What do you think?
Again?
What do you think if in the next future, I mean your observatory will build some MT monitoring in the front of the Taal volcano?
Yes. I've been proposing to again install magnetometers, real-time magnetometers, and of course a flux gate magnetometer with earth resistivity meters to essentially using a magnetotelluric instrument to monitor the resistivity underneath Taal volcano. But at the moment, we're still rebuilding most of the monitoring stations on the island. Was destroyed during the eruption. So at the moment, we're concentrating mostly on ground deformation and seismometers to rebuild the monitoring network. So unfortunately, electromagnetics is not a priority, but I do have some instruments to use.
Okay. Ada lagi yang mau bertanya? Still have question for Dr. Alanis? Please raise your hand. Bisa juga bertanya dalam bahasa Indonesia, boleh. Oh, please. Okay, the next question from Dr. Hasib. Please,
Okay.
Dr. Hasib,
Thank you.
yours.
Thank you for the time. Okay. Thank you for the interesting and insightful presentation, Dr. Alanis. So my name is Muhammad Hasib, and I'm from the Research Center for Geological Disaster, BRIN. So as you mentioned before that regarding on the eruptive behavior, you said that sometimes we have unstable condition of the Taal volcano's eruption. So my question is that, in your opinion or perspectives, how such a change of the eruption style happen on volcanoes, and what is the factor or parameter that is most contributed on the change of the eruption style? That is my question. So
that's an interesting question, because of course, as a volcanologist, we are always looking for the parameter that is commonly associated before an eruption. Of course, the eruption style has to be constant. I remember right now I'm working at Mayon volcano, and the eruption style of Mayon volcano is similar to Merapi type. But recently, the eruption style changed for Mayon volcano. So the previous model that we use is no longer, more or less, not applicable anymore. I think the change in eruption style is likely due to gas content. So in the case of Taal volcano, these volcanic gases were accumulating inside the hydrothermal reservoir, particularly the sulfur dioxide. So now that the hydrothermal reservoir is gone after the 2020 eruption, most of the sulfur dioxide coming from the magma is free to escape into the air. So Taal volcano is no longer a closed system, but what we call an open system. So, and likely because the hydrothermal reservoir is gone. So at the moment, we don't know if is it totally gone or is it forming again. And with the large amounts of volcanic gas, sulfur dioxide being emitted almost every day, yesterday it was about 2,000 tons. So it's likely that there is no hydrothermal reservoir underneath Taal volcano right now.
okay, thank you. So it means that the gas is the most contributed on the eruption style happen.
Yes.
Oh, okay. Thank you for your discussion.
Welcome.
Okay, thank you, Dr. Hasib. Still more question for Dr. Anis. Oke, untuk teman-teman mahasiswa yang mau bertanya boleh. Ini kayaknya ada perwakilan beberapa kampus. Silakan dalam bahasa Indonesia juga boleh. Jika ingin bertanya tentang gunung api dan metode Magnetotelluric, silakan.
Ibu Fepti, ada yang dari chat?
Oh, chat ya. Oke. Coba saja. Oh, Pak Yan. Oh ya. Okay, the question from Pak Yan. His question is, are there ways to overcome the limitation of the data processing below 0.01 Hertz?
Okay. The only suggestion was to get more data outside of the volcano island. That is, get measurement points along the caldera. Beyond that, I don't know how else to utilize the data. I think it's possible to still utilize the data, but again, we have to take into account the coastal or seawater effect.
Okay, yes, you are right. I think the news publication from Dr. Yahmaya. I think I forgot the name of the study area. To overcome the limitation because of the seawater, he used 3D by consider the resistivity value of the seawater in the 3D modeling, and the modeling is success, I think. So he can use the data below 0.01 after considering the seawater resistivity value in the 3D modeling by using the Siripun Parapun code. Maybe
yes.
Maybe you can apply the 3D modeling. So the remodeling the empty data, and we can see the new subsurface modeling by using the 3D modeling, and after considering the resistivity value of the seawater.
Yes. Thank you very much.
Okay. Yang lain mau bertanya boleh nih dari adik-adik mahasiswa. Bahasa Indonesia juga boleh, silakan. Okay, our time is until about 11:30. Is it right, Pak Tugi? If there is no question, maybe we can go to the photo. Okay. For the all participants, please on your camera. We want to we take picture together. So, Patiti yang akan ngambil fotonya.
Baik, mohon di kameranya dibuka ya Bapak Ibu untuk laporan. Mungkin ini ada 4 kali take ya, mungkin kita mulai dari halaman pertama ya.
Oke, yang belum kameranya di on kan boleh, silakan.
Ya, yang kedua. Yang ketiga.
Progress.
Oke, terima kasih Bu Febri.
Okay. Thanks very much, Dr. Alani, for your presentation. I think it is the interesting presentation for us in Indonesia, because as we know, geologic setting of the Indonesia somehow same as that of the geologic setting of the Manila. We also have some volcano. We also have some earthquakes occurred in Indonesia. Thanks very much, Dr. Alani. It's nice to meet you. I hope we can meet again, not online but offline in the future somewhere.
Yes, of course.
Okay.
I have one request.
Okay.
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 Could you send me the how many participants, or just the number of participants?
Okay.
Who attended? Yeah.
Okay. I will send to you by email the
just the number. It's okay.
Just the number. Okay. I will send email to you. Thank you very much, Dr. Alani.
Welcome. Keep safe, everybody.
Okay. Terima kasih
still
semuanya. adik-adik mahasiswa, Bapak Ibu semua, kita akhiri ya presentasi kita hari ini dan sampai ketemu di webinar selanjutnya.
Baik, terima kasih.
Recording stopped.